from last time, we took a look at the whole idea about areas and volumes transforming through a linear transformation. Here's your information over here where we have a transformation determined by this diagonal matrix ABC, and we want to know where the sphere, actually when they say the ball they mean really that three-dimensional sphere, and where that thing gets transformed to. And then they want us to prove that this actually gets transformed into an ellipsoid, a three-dimensional ellipse. And the volume is, well, they want us to find the volume. So a solution that I came up was the idea that if we have any x value, should be a vector. No, it's not going to do it if it's boldface. Any x value, by x vector, I mean x, y, z. So we want to know what happens when we attach it or when we apply the matrix to it. And when we apply the matrix to it, basically it gets sent to ax, by, and cz. And if you put those values in for x, y, z into the ellipse equation that they have, you're going to get back your x squared plus y squared plus z squared is equal to 1. So that shows that those two things, the ball actually gets transformed into this ellipsoid. And then the other thing that it's asking us is to find the volume of the ellipsoid. And if we know the volume of the sphere, then we just need to find the determinant of A, or of the transformation, and that's going to give us the volume of the sphere or the ellipsoid. So if you look up the volume of the ellipsoid, you'll see that it's actually 4/3 pi times A, B, C. Okay. If A and B and C are all equal to each other, let's say R, then this is 4/3 pi R cubed, which is the volume of a generic sized sphere. Okay. So this was in the notes already, and this is just a little bit of explanation that I can give you. Suppose you can if you want. I can't think of an example off the top of my head. So because this is really being done in so yeah, the polar coordinates is not a linear transformation, so I don't think we can use that here. We can use approximations to linear transformations, which is what happens when you change variables in polar coordinates, but we don't. Yeah. The other thing I was asked to talk about was just to talk a little bit about the assignment and the worksheet or whatever it's called. Yeah, I guess it's the worksheet, and what to do in Octave or in MATLAB, whatever you're going to use. So the idea here is to come up with this matrix and find the LU decomposition, and then use that LU decomposition to solve for this. And use the LU decomposition to solve for AX equals B by taking it into 2 steps, which seems more work if you have MATLAB, since you can just find the inverse of something. But I think this is just a good process, a good practice to to work on MATLAB. And so this is a general idea. So what I could do is I could tell you what I would like to see, at least. If you have your Octave or your MATLAB up, you can first define your matrix. So let's say my matrix is it's a tridiagonal, right? What's that matrix? Yeah, so it's got the diagonal strip and it's got another above and below the diagonal. It's got values, and so let me make up a generic tridiagonal. This is 5. Let me make one smaller. Let's do 4. So just do your matrix. 5 minus 2, 0, 0, and then minus 2, 5, minus 2, 0, and 0, minus 2, 5, minus 2, and 0, 0, minus 2, 5. I hope that's a tridiagonal. So it's got 5s down the diagonal, negative 2s up and below, above and below. So the LU decomposition is the function called LU, but there's some functions in MATLAB where the output has two different it has two different outputs, and so if I just say LU decomposition of A, then I'm going to get some value. So let me see, LU of A, and I'm going to get this matrix, which doesn't seem like it's an upper diagonal or a, so the command is to put L and U, and then LU of A. So here I'll have actually two matrices, the L matrix, which is a unit lower triangular, and an upper triangular matrix. And if you notice, the information found in the L and the U, I don't know if you noticed, was actually combined in the LU output here. Interesting, right? Because the diagonal for the unit triangular, lower triangular matrix, I don't know why it has this. Lower, upper, it's like the LU decomposition. Well, if you don't partition it to the different parts of the output, then it's going to give you one matrix where the L and the U are combined. And let's take a look at the important informations for the lower triangular matrix. The diagonal of the lower triangular unit matrix is all 1s, right? So that information is not important. And then so what's important is the upper triangular and the lower triangular parts of the output. And so what they do, if you just say LU without putting it all together into, or without separating it, is that they put the output together in one matrix, since that one matrix can hold the information for both matrices. Because zeros, so the upper triangular matrix is zeros in the lower part. And so they put the lower triangular matrix information in that lower part. Because it's all 1s. You know it's 1, they know it's 1, so it's not important. Just what is important is that what's going on with my outputs. I don't know where I am anymore. That's okay. Let's go back to our output here. Forward. Yeah. So here's my L matrix and my U matrix. And if you notice, they call this a bidiagonal matrix. It's just a strip. in the diagonal of two, I don't know how to say it, two strips down the diagonal. It's zeros everywhere else is what I'm trying to say. So a tridiagonal matrix gets broken up into an LU that are both bidiagonals. All right. So if I want to put as an input or an output, I have to make up pretend. I have to pretend that I have a different value matrix. Since this is a 5 vector, I need a 4 vector. Since my example is a 4 by 4, and so I want to run it through this process where I find T1, T2, T3, and all that. And so what I need to do is I need to solve for the inverse of the lower triangular and the upper triangular matrices. And so the upper triangular goes first. Which one goes first? I think the lower triangular, LU. So I have to find the lower triangular result first, and then the upper triangular result. So I'm going to set T0 to be some vector, and I need it to be a column vector for this to work out, right? So I'll make up another set of numbers here, 10, 12, 12, 10. And then so I'm gonna, that's my T sub 0. I'm gonna find my Y sub 1 by solving for Y sub 1 here, which means I need to apply T sub 0 to the inverse of the L matrix. So I'm going to say Y sub 1 or Y1 is going to equal to the inverse. What is it, INV or the whole thing? I think it's INV, right? So INV of the L matrix. Okay, so I'm going to get the, oh, shoot. Let's try that again. Y1 is going to be the INV of the L matrix, and then I actually need to multiply it with T sub 0. There we go. So that's my Y sub 1, and then I'm going to try to find my T sub 1 vector. T1 is going to equal to the same thing, except I want to apply it to the U vector. So it's the inverse of U that's being applied to the Y1 vector that I just found. So that's like the L vector, or the inverse L. And then I have T sub 1. So I'll do that to find T sub 2, T sub 3, T sub 4. I'll do that in several steps. Okay? So that's how you do this. Now, in terms of what you want to submit, or what I want you to submit, I essentially want you to submit all the commands that you put in, and if you can also submit all the outputs, that would be great too. So my suggestion would be just to scroll up your command window and copy everything. Can you scroll up? Control Alt? No? Well, if you can't do that, then just get it from your command history. So you get the commands from your command history and then just paste it on. I'd actually like to see the outputs though. Any ideas on how to get all the stuff in your command window? I don't know. I want to copy. Well, I just want to copy and paste the command window, everything in the command window. I, I, I can't seem to scroll up any farther. So I'm here. I could do Control A. Yeah. Right click. What? Oh, there it goes. Oh, maybe. So let me copy that and see if I can paste it onto a Word file. Oh, there it goes. TXT would be fine. So yeah, you could also select everything and then make this into an evenly spaced font so that it looks a little bit nicer. Hey. Well, I was looking at this, right? So there's a couple of things where I tried some stuff out and then it this is what I was talking about earlier, the LU without assigning the lower and the upper triangular matrices. And so if you look at it, it has the diagonal and it has -2 and -4 point something. And then compare that with the L. It's got these things now. So we want to get rid of some of those. Especially if yours does that. So if you look at the LU decomposition of the actual L and the actual U versus the LU decomposition without the L and the U being separated, you can see that they put the information all in one matrix here, which could be a little confusing. And so if you have it separated, if you have done it correctly by doing this command, where you assign the L matrix and the U matrix, then you can have that here. And then this is my T vector, my Y1 vector, my Y, oops. So this Y1 didn't work out. I'll get rid of this command and output. And then I have, oh, I don't know what this is. So this would be my text file that I would save. So I think I would just, put my name on and then this is the text file, or this is the file that I would submit. I would like for you to submit. Okay, so it has the commands that you used and the outputs. And then if you want to make it look a little prettier, that's fine. But at least either save it as a text file or you can adjust the font to a font that would be readable in like a computer programming setting. Okay. Worksheet number 3. 4? Oh. Oh, so this should be 4? Well, sorry. Yeah. No, the T1 is here, and then you're gonna get your results for T2, T3, T4. T1, T2, T3, T4. So this is the original matrix that you start with, and what this is saying here is that to find T1, you have to let this be T0, and you get Y1, and then you get T1 from here. And then that'll be the T1. And then you'll use your result for T1 to do this process again to get T2. Right. And so if you want, you can write a program that does that automatically and just spit out all the outputs for Y1, Y2, and then T1, T2, and all that. I don't know. Oh, I still forgot you. You're supposed to email me about that. Okay, I'll do that, and then I'll try to get the grades all figured out over spring break. Okay, any questions about this? Are you sure this is worksheet 2, 3? Okay, so I need to adjust my other worksheets. So this should be 4. That's, yeah, that's already confusing enough for me. 4. Okay. So then I should adjust my other worksheets. So this is worksheet 5. And this is worksheet 6. So I'm going to give you, I was going to do this all in one worksheet, but I decided to split it up so we have more worksheets to do. So instead of 4 worksheets or 4 problems in one worksheet, I split this up to 2 problems in one worksheet for 2 worksheets. And it's about inverses. Oh, man. Oh, this is really confusing. All right, that's enough of that. So hopefully that's kind of clear in the worksheet, and this is more exploration for you to do using Octave or MATLAB. It'll get you kind of used to doing stuff with it. All right, we should probably move on. Today is 19th. Yes. Well, we talked about it. We're going to jump past vector spaces since we did kind of talk about vector spaces already. Chapter 5 or chapter 4 is vector spaces, and then kind of like some tidbits and information about vector spaces applications, which would have been a nice chapter to do, but I feel like we're kind of running out of time, and we did talk about column space, null space, and rank and nullity and stuff already. So they kind of reiterate all that stuff in chapter 4, and then they splatter on all kinds of other applications. So instead of going over chapter 4, we'll just jump to chapter 5 so that we can see some more interesting stuff towards the end of the class, like orthogonality and Gram-Schmidt orthogonalization process. That would be more interesting. So chapter 5 is all about eigenvalues and eigenvectors. So anybody speak German? I think that's a German name, isn't it? Eigen. Self. So self or self-scaled, because an eigenvalue and an eigenvector are related in such a way that if you apply a matrix to that special vector, then you're essentially going to get that vector or the scaled version of that vector. And that's what that says. So an eigenvector of an n by n matrix, it has to be a square matrix, is a non-zero vector such that ax is equal to lambda x for scalar lambda, and the scalar lambda is called an eigenvalue that corresponds to that eigenvector. So I had some examples of this. I didn't prepare. What does? Oh, yeah. Let's see. Let's see if I have my own pictures. Chapter 5. What is this? That's no good. I have one that has pictures. Student stuff? No. Class notes, class examples. No, maybe it's in an older one. Eigenpicture. That's about as good as it gets, right? What's this? There's a cosine in there. There's sine and cosine. All right. So what we have here is a matrix, 2003 matrix, and what we have here are arrows. Are arrows that spread out, and so what we could do, or what I can do, is how come I should just attach this over here? Is I can have an arrow. The black arrows that are coming from the middle are arrows that go from the origin. It has unit length, and it's just going around in a circle essentially. And so the red arrows are what happens to these vectors when I apply it to the matrix. Okay, so the vector 1, 0 gets applied to this matrix 2, 0, 0, 3, and then we get, let's use this as an example. Let's put it in our notes and see if we can make sense out of it. So just to let you know what this picture means, this picture has the matrix, what was it, 2, 0, 0, 3? And then what it does is it just takes random vectors, and these are just vectors, kind of unit long vectors that are going around in a circle. And that's the sine and cosine. That's what the sine and cosine was about. So it takes, for example, this vector. This is the I vector, 1, 0. And then you apply a of 1, 0. And then you're going to get 2, 3. No, what are you going to get? 2, 0. So if I apply 1, 0, all right, let's actually. Two, 0, right? So that's this vector here. And what I did with a vector is, with the output vector, is that I just, instead of having it come from the origin, I just put it at the tail of the original vector, just so it doesn't get too confusing. And so in this particular case, we see something interesting in that 1, 0, a of 1, 0, is actually equal to 2, 0, and that happens to be equal to 2 times 1, 0, right? So in this particular case, we have an eigenvector, and then we have an eigenvalue, corresponding eigenvalue. Now, if I just take another random one, this is like, then it's probably not an eigenvalue. So let's take this vector over here. I'm just going to call that vector v. So, and then this vector over here is the vector a applied to v. And so if you take a look at it closely, you can see that it doesn't fall on the same line. It's not linear, collinear, right? So then AV in this case cannot be equal to any scaled version of the original vector v. And so you can say that this v is not an eigenvector. Okay. So the point of this graph, or this picture over here, is that we can kind of find, just by eyeballing it, we can sort of find where our eigenvalues or eigenvectors are. And then how much they get stretched out will decide your eigenvalue. And so I think I had 36. If you take a look at that, you try to see, they're really close, but can you immediately tell where the eigenvalues are, or eigenvectors? Yeah, just at those places. Oops. That's the PostScript code of the output that we don't want. Just want the picture. So it may or may not be obvious, and it's kind of hard to tell with these pictures, but it looks like the eigenvectors are those vectors along the x and the y axis. So eigenvectors look like they're just going to be 1, 0, 0, 1. It looks like the -1, 0, 0, -1 also, right? Yeah. They're not important. So all these others kind of bend through, and so it's not collinear, so it doesn't work. And also, I put 4 eigenvectors here that we happen to have found, but it turns out that if we only want a linearly independent set, and so we're going to just focus on one of these pairs instead of all 4 of them to be our eigenvectors. Okay, so we'll talk about making a basis. Remember, a basis is a set of vectors that span something that all have to be linearly independent. So we'll be talking about a basis for your eigenvector or eigenspace, it's called. Let's see, do I have more pictures? Oh, I have this picture. It has sort of an animation. So this is a different matrix. This is a 1, 1, negative 1, 3 matrix that looks like it has a little bit more interesting bends. And then you can see it. You can see where the possible eigenvectors might be. So this clearly is not, right? And then if I move my, so this looks like it's going to be 1, maybe. That one looks like it's going to be 1 also. Oh, so it's, yeah, one of these two. This one? It's only 12. Let's make it 36. Then you get a nicer picture. Not responding. Matt? Not necessarily. You might just get 1. You can't have more than 2. Yeah. Yeah. I changed my A matrix. Well, the eigenvector is attached to the matrix itself. So if you change the matrix, then you change your problem. So you start off with the matrix, and then you have to figure out what the eigenvalue is. All right, now it's broken. So anyways, this was done in 2 dimensions because 1, it's easy to visualize, and 2, the vectors that we could talk about are just vectors around the circle. If we try to do this in 3 dimensions, then it could be any vector that's within your sphere. Those would be the vectors to view, and then that would be a little bit more difficult to look at. But anyways, this is one view of an eigenvalue, an eigenvector. And now it's crashed. Goodbye, Mathematica. All right. So let's see, what else can we say about eigenvalues and eigenvectors? Here's an example. I have the solutions here already. An eigenspace, so if lambda is an eigenvalue of A, if and only if the equation has a non-trivial solution, and instead of all solutions to the null space of this matrix forms a subspace, and that's called the eigenspace. So let's do this as an example. Find the eigenspace of this. So if you want to find the eigenspace, they say that the eigenspace is really the null space of this matrix. So we have the matrix A. We can create a new matrix. Let's call it B equal A minus lambda I. So lambda is equal to -2 in this case, A plus 2I. So that would be the matrix 1, 0, -1, 1, minus 3, 0, 4, -13, 1, minus or plus 2, 2, 2 in the diagonals, and then zeros everywhere else. So your new matrix B is added. So that's 3, 0, -1, 1, 0. Negative what? Oh, negative 1 and 0, and then 4, negative 13, and 2, 3. All right. So the null space of this is going to give us the eigenspace. So let's find the null space of that. I remember how to find the null space. It's all the vectors that get sent to 0, right? So it's like this thing with the 0 augmented. So let's just row reduce that. 3, 0, minus 1, 1, negative 1, 0, 4, minus 13, 3. Negative 3? What? Well, Kramer's rule would just be zeros in the middle. So I think if you just row reduce, then that would be easier than Kramer's rule. Can we just punch it into? We do have. Although if we start getting fractions, I'm not. You're there. So B equals 3, 0, minus 1, 1, minus 1, 0, 4, minus 13, 3. This looks like a 1/3 maybe. Or you just call it a 1/3? Yeah. Negative 1/3. So 1, 0, negative 1/3, 0, 1, negative 1/3, and then zeros on the bottom. So if you're expecting an actual value here, right, you should, if you're expecting a non-trivial solution, you should expect to have zeros in the bottom row. So we have a free variable. The third one's a free variable. And then so x3 is free. x2 is equal to positive 1/3 x3. And then x1 is also 1/3 x3. So it looks like our possible eigenvector. So I'm just going to call it E vector, eval, E vector, eigenvector, eigenval. So this is equal to 1/3, 1/3, and 1. What? So this is the basis for eigenspace. This particular eigenspace for this lambda. So I can just scale this, right? This is x3, so I can just scale it as 1, 1, and 3. Usually nicer to look at. So an let's call it eigenspace. So the eigenspace of A corresponding to a particular eigenvalue is going to be the span of 1, 1, 3. Yeah. This is an x3, sorry. Oh, this is a t. I just changed the variable, rescaled it. Yeah. Yes. No, this spans the space for the eigenspace for lambda is equal to. So this only spans this is a one dimension. There's only one of them, so it's a one-dimensional line. So that line is the eigenvector for lambda is equal to -2. Well, no, it's a one-dimensional subspace of R3. So this is an R3 because we're looking at 3 by 3 matrix. And so your eigenspace in this case for lambda is equal to -2 is going to be a line spanned by this vector in 3 dimensions. Okay. All right. So that's the eigenspace business. Yeah, we got it correct. That's good. So a couple of short theorems that are going to be stated without proof is the fact that if you have a triangular matrix, then your eigenvalues are exactly what's in the middle or the main diagonal. And then if you have a set of eigenvectors that correspond to, each of them correspond to a distinct eigenvalue, then all those different eigenvectors are all linearly independent from each other. Yeah. Well, it's the null space, not of the original matrix. It's a null space of this new matrix. And so that's the tricky part, is that this is what we're actually looking at. We look at this A minus lambda I as some new matrix, and the null space of that matrix is the eigenspace. Okay. All right. So a couple of theorems. If we have a triangular matrix, then it's easy for us to find the eigenvalues. And if it's not a triangular matrix, then we're going to need to work a little bit more on finding the eigenvalues, which for some reason they don't talk about in this section. They're going to talk about next section, but we'll get there in a couple of minutes. Okay. It's innerly. I usually do. I have the spell checker on while I'm typing, and then I turn it off. I don't know why it's not there. Yeah, yeah. So if you have a triangular matrix and a 3 by 3 matrix, then you have those eigenvalues. Well, technically, it's already row reduced if it's in row echelon form. Oh, so the row reducing, if you row reduce that does not include any scaling of the rows, then it would be okay. Yeah. When you start scaling the rows, that's when you start changing the eigenvalues. Good question. What's the point of an eigenvalue? It gives us more information about the matrix and the different spaces. What? Well, well, well. in an application that we're not planning to do in this class, we can solve for systems of linear equations. Let me rephrase that. We can solve for systems of linear differential equations. And then if we have, and here's an example that I saw in one of the workshops that I went to. There's these two springs that are dependent on each other. And so as they move certain ways, they have relationships with each other. And so to solve for that, you would create a 2x2 matrix. And then in the 2x2 matrix, you can figure out the direction in which they're related, dependent, or whatever. And then that's the eigenvalues and eigenvectors give you the direction. Yeah, yeah. And the direction, too, that the relationship is happening. Okay. So you can also apply some of this stuff with graphics. I think computer graphics, they do eigenvalues and eigenvectors there as well. There's also in statistics the whole idea of stochastic Markov chains and stochastic matrices. I think we might touch on that a little bit if we have time. I think it's covered in this chapter also. Okay. All right. So let's find out more about eigenvalues and eigenvectors. Characteristic equation. So I don't know why they decided to wait to talk about the determinant relationship with a matrix, but this is where they talk about the determinant not being 0 and then the matrix is invertible. Any case. Yeah. Yeah, they have a theorem about it, but they didn't pull out that big long theorem until now. So here the determinant. So we're going to talk about our matrix A and then reduce it to an upper triangular matrix, which is in row echelon form. And this row replacements and row interchanges. And then this is the without scaling part, Brian, that you asked about. So as long as we don't scale any of the rows, then this particular way to compute the determinant would work. So it turns out that if you row reduce something, you can find the determinant by looking at just the product of its diagonals. And then you also, if you happen to do any row swaps, then you account for that by a negative sign. So if you do one row swap, then that's one negative sign. If you do two row swaps, that's two negative signs, which is a positive. And so if you count the number of row swaps that you do, and you take that as a power of -1, that will account for the row swaps. And then the row times another row added to another row, that stuff doesn't add on to the determinant, if you remember. And so your final result would just be an upper triangular matrix, and then the determinant would be the product of those diagonals. If one of those diagonals happen to be 0, then the product will become 0, and then you'll have a 0 for a determinant, which according to that theorem that we had says that your matrix is not invertible. So also an upper triangular matrix or any triangular matrix, the eigenvalues are all the diagonals. So if you happen to have a 0 in a diagonal, then your determinants equal 0, and then also your matrix is not invertible. Yes. No, not in general. In general, if the determinants equal to 0, then we just say, oh, it's not invertible. R is the number of times you swap the rows if you do any row swaps, if you do any at all. I've tried to avoid row swapping. Yeah. Yeah, you're not allowed to scale here. I mean, if you scale, then you just have to compensate for that. Yeah, but that gets more confusing if you do it that way. Because scaling will change your determinant. Yeah, so if you swap, then your determinant will have a minus sign. If you scale, then you're starting to introduce numbers to change your determinant. Now you can adjust for if you want. So here's that long theorem. I think we went A through M in the beginning, and then we added M through R, and now we can add S and T. And the T is really from from chapter 3 when we talked about determinants. So if your determinant equal to 0 is equal to 0, then it's not invertible. If it's not equal to 0, then you can find the inverse. And then the eigenvalue business kind of carries over from that last definition and then the theorem before that says that if 0 is not an eigenvalue for your matrix, then it's going to be invertible. Okay. So as you're doing these computations, it is possible to get 0 as an eigenvalue, which means your matrix is not invertible. Okay. So I just wanted to show you this complete theorem. You just have to write S and T here, and it's continuation from the invertible matrix theorem. All right, what we really want. These are more properties. Do I want to? I guess I'll list it since it's actually covered in the book. What we really want to get into is the characteristic equation. And the characteristic equation, well, before we get there, just remind you of some properties of the determinant. If it's equal to 0, then it's not invertible. If it's not equal to 0, then it is invertible. The determinant of the product is a product of the determinants. Determinant of the transpose is equal to the determinant of the original matrix. If you have a triangular matrix, then determinant is a product of all those. And then determinants of the basic row operations here talk about how it doesn't change if you do the row times and then add it to another row. It'll be a change in the sign if you switch one row with another, and then if you scale one row, then your determinant is going to get scaled as well. All right, so these are old theorems about determinants back in chapter 3, and some of them are easier to prove now with some information that we have. But what we really want to get into is this characteristic equation. So the characteristic equation is going to be the determinant. This is where the determinant comes in. A characteristic equation is the determinant of that matrix. Remember, we found the null space for that matrix. So if we create this this matrix where lambda is a parameter or an unknown variable, then you have a characteristic equation. It's really a characteristic polynomial because it'll end up being a polynomial in lambda. So when we have a polynomial, the solutions for the polynomial would match the degree of the polynomial. In other words, if we have a third degree polynomial, then we should expect 3 solutions. So the solutions might be repeating. in which case they have what's called an algebraic multiplicity. And then in some cases, those solutions might be complex conjugates, complex numbers. And so for those, we can talk about those possibilities later on. But the point is that your characteristic polynomial should have roots, solutions that match the degree of the polynomial. And the degree of polynomial should match the dimension of the matrix. All right, so let's do an example. There's an example here. Ooh. Why is this first? Oh, because it's a triangular. That one's going to be easy. Let's do number 16 first. So here's an example. We have a lower triangular matrix. So the determinant of any triangular matrix, remember, is just the product of its diagonals. So what we want to do, if this is A, we actually want A minus lambda I, which is going to be this 5, 0, 0, 0, 8 minus 4, 0, 0, 0, 7, 1, 0, and 1 minus 5, 2, 1, minus lambda I, which is just the identity matrix with lambdas in the diagonal, and then subtract. So we're going to have 5 minus lambda 0, 0, 0, 8, and then we have negative 4 minus lambda 0, 0. We have a 0, 7, and then we have a 1 minus lambda, and then we have a 1 minus 5, 2, and then 1 minus lambda. So what happens here is that I want the determinant of this. And that's just going to be the product of the diagonals. 5 minus lambda, minus 4 minus lambda, 1 minus lambda, and 1 minus lambda. So this is your characteristic polynomial. You can, but it, well, in a lot of cases, you want to solve for this when this is equal to 0. And when all you have is this, then it's already in factored form. It's really nice. Okay, but chances are it's not going to be a nice triangular matrix, and so you'll have this thing minus some other various numbers which you can't easily solve for without actually expanding everything and trying to factor it. So we have lambda is equal to 5. Is that right? Negative 4 and 1. And note that lambda is equal to 1 has multiplicity 2 because it happens twice. So that's an important thing to keep an eye on also, is the multiplicity of your eigenvalue. Okay, yeah. You're gonna have 4 solutions, yeah. So here I have 3 distinct solutions and one of them repeats. All right, let's do another one that's not a diagonal. Number 6 maybe. Nope. Copy, paste. All right, 3, negative 4, 4, 8. Let's do this business to it. A minus, change colors. a minus lambda I. And once you start getting used to it, you'll see that, just remember that the only thing that changes is that diagonal. So 3 minus lambda, negative 4, 4, and 8 minus lambda. So what do we get? The determinant of this is going to be the diagonals. So 3 minus lambda, 8 minus lambda, and then minus negative 16. So here, again, we want to set it equal to 0 to find the eigenvalues. And so if we try setting it equal to 0, don't bring the 16 over to the other side and then split it up that way, right? It's a quadratic, and so you have to FOIL everything out. 24 minus 11 lambda plus lambda squared plus 16. And so lambda squared minus 11 lambda plus 40. Is that right? So you could say that this is your characteristic polynomial, and then finding the zeros of this would help you find your eigenvalues, eigenvectors. So I think this might have complex roots. Would it? E squared minus 4ac. Yeah. So we might have complex numbers for this one. Any questions? Characteristic polynomial as your roots. Yeah. Yeah. You might have sines and cosines involved again. All right. Similar matrices. I think those are oh yeah, let's think about that. Yeah, so the tricky part about this is that we want the determinant of this thing, right? So these things have lambdas in them. So to try to reduce it is a little tricky, right? Because you have to multiply, you have to divide this by something with a lambda and then get rid of that. So trying to row reduce would be difficult because of lambdas. So if we know what lambda is, then finding the determinant would be easy. But if we don't, but then if we know what lambda is, we probably don't need to find the determinant. No, because then the matrix would be different. All right. All right, so one last piece of information from this section is the similar matrices. If A and B are similar, then there exists this invertible matrix. You can say that P1 or P inverse times A times P is equal to B. And we usually say, I don't know if they do this anymore, since they kind of use this squiggly for row reducing or row equivalent. But that's what I remember using for similar matrices. So if two matrices are similar, then we write this. And then there's all kinds of other theorems too, or not theorems, but properties to say that this is like an equality. It's what is it? Symmetric, reflexive, and transitive. You remember those? So A is similar to A, and then here if A is similar to B, then B is similar to A. And then if A is similar to B and B is similar to C, then A is similar to C. So the first one is called symmetric. It's itself, and is that reflexive? I think it's reflexive. The second one is symmetric, and the third one is transitive. Anyways, you could do simple proofs with that with a P, because they just say that there exists some invertible P matrix here, so we can figure out what P is for these things. So once we have that, and since we are talking about characteristic polynomials, if A and B are similar, then they have the same characteristic polynomial. And if they have the same characteristic polynomial, then they must have the same eigenvalues with the same multiplicities and everything. Yeah, sure. So there's some cool proofs for this. I mean, these are simple proofs. So let's take a look at one of them. So if A is similar to B, then according to this theorem that says A is similar to B, and we can write this one. A is equal to B with a P's in between. And so to say that B is similar to A, we can just multiply both sides by P inverse on the one side, on the left side, and then multiply it by P on the other side. But this P is actually P inverse inverse. And so your kind of new invertible matrix P is actually P inverse. And then this will show that this is symmetric. So anyways, the next section, we talked about factoring matrices with the LU factorization. This is another way to factor a matrix, but it's going to factor a matrix in a special way. It's going to factor in the matrix as a new matrix with two other invertible matrices. So you're essentially factoring it in three matrices. And what's going to be special, we're going to look for a special factorization to find the similar matrix where the B in this equation is actually a diagonal matrix, because we know how to find in the determinants of diagonal matrices, right? So this is going to be called a diagonalization process. Yes. Yeah, which is another way to relate matrices. So instead of going through the process of a row echelon form and getting an upper triangular matrix, we're going to factor it this way, where we actually get a diagonal. All right.